Lolo. Deux, un, deux, un, deux, un, deux, un, deux. Hello Peter, can you hear me? Hello, hello.
J'ai menu, ça marche? J'ai menu. Ah, tu veux dire qu'il y a... Oui, c'est ça. Par contre, c'est pour Zoom.
D'accord, ok. Ça, c'est Zoom, mais ça... Ok, parfait.
Good morning, everyone. Thank you for coming to this new colloquium of IPhT. And today we have the great pleasure to receive Vincent Vénin, who's coming from École Normale Supérieure in Paris. And so just a short bio. So Vincent and I did our PhD together actually at IAP. So you defended in 2014, I think?
Right.
Yes. Afterwards, you went to Portsmouth at ICG for a postdoc, and you were hired very quickly by the CNRS. Congratulations. So yes, Vincent is an expert on the quantum origin of on the early universe, and in particular on the quantum origin of the fluctuations of density of the universe that led to the structures that we know today. This is what you're going to talk about today, and so thank you. The floor is yours.
Well, thank you very much, Pierre, for the introduction and for the invitation to come and talk here. And thank you all for coming this morning. So indeed, I'm going to talk about the production of fluctuations in the early universe from quantum mechanical processes, and whether we can prove that the density fluctuations we see in the universe today comes from quantum fluctuations rather than from another type of fluctuation. So because I know that people in this room work on different topics, I'm going to spend some time in the beginning trying to introduce the motivations in a pedagogical way. But if you have any question or if there is something you want to ask, please don't hesitate to interrupt me at any time. Okay, if I don't have time to show all the slides I've prepared, it's completely fine. I can stop at any point, pretty much. Okay, so the question I want to ask today is related to the formation of density fluctuations in the universe. Here you see a small movie from a simulation, numerical simulation, which is called Horizon, which simulates a certain box in the universe, and where you see that small density fluctuations grow under the action of gravity, and they give rise to this web structure in the universe where matter is organized along filaments and structures and so on. And that's the way that we understand the formation of structures in the universe today. All those structures, they come from tiny fluctuations, primordial fluctuations that are the initial conditions of those simulations. And the topic I work on is how can we understand the origins of those fluctuations and where do they come from. So the way that we understand them is through quantum fluctuations, which is a process that we know very well and that we have encountered in many different situations in physics, including in the lab. So the typical example, which has nothing to do with cosmology, is the following. So we know that from the vacuum we can have a spontaneous creation of pairs of particles. And because of Heisenberg uncertainty relation, the energy which is contained in this pair of particles is related to some timescale, and typically this pair of virtual particles can exist over a certain timescale, which is given by Heisenberg's principle. And after this timescale, they will just annihilate, and there will be no net creation of particles. But now if you put this vacuum box into a strong electric field, for instance, if you apply a strong electric field and you create this pair of virtual particles, if they have opposite electric charge, they will start to move along opposite directions. And if after the timescale delta t, those two particles have moved to completely different locations in the box, then they cannot annihilate again. And then you have created, what it means is that you have created those particles, they become real particles. Okay, so this effect is known, it's called the Schwinger effect. if you apply a strong electric field to a vacuum, to some vacuum, then you create particles. This is also true if you apply a strong gravitational field, and that will be related to the Hawking effect. And this is also true if you consider the case of an expanding background. Right? So the idea is that in an expanding background, you also create virtual pairs of particles. And because of the expansion, those particles start to move away one from the other. And if after the time delta t they have sufficiently moved apart, then those particles become real particles, and you have created particles out of the vacuum. Okay, so the idea is that this is exactly what happens in the early universe. So this is a sketch of the evolution of the universe as we understand it today. And there is a phase very early on, which is called cosmic inflation, during which the size of the universe grows at a very quick rate. And that's such that the mechanism that I was talking about is very efficient, and you have a lot of creation of particles. Of course, this is here sketched in a very simple way, but then I will be a bit more specific. So the idea is the following. So inflation is a phase where the scale factor, which is the parameter that appears in the metric that describes the universe, is accelerating. So A dot positive means an expanding universe. A double dot positive means accelerated expansion. So during this, so in this metric, you can define a single dimension full parameter, which is called the Hubble parameter, A dot over A. So 1 over h has the typical timescale of time or length. And so if you consider some quantum field on top of this, or even some classical wave on top of this expanding background, and if you Fourier expand this field into different Fourier modes, then what you find is that the physics of each mode very much depends on whether the scale associated, so the wavelength, is either smaller or larger than the Hubble radius. So if it is smaller, it means that locally you don't feel the effect of space-time curvature. It's a bit like if you make measurements in your lab, you don't have to take into account that you work at the surface of the Earth, which is curved. Okay, so in that case, the physics is the same as in flat space-time. And in this limit, this limit is easier to work in because we can define, for instance, vacuum state. It's exactly as quantum field on Minkowski background, right? So everything is pretty unambiguous. But then there is the other regime where the wavelength is larger than the Hubble radius, which measures the curvature of space-time. And in that regime, you need to take into account that you work on a curved background, and typically you have this quantum particle creation mechanism that takes place. Okay, so that's analogous to the Schwinger effect I was discussing. Particles are being created in this regime on the right-hand side. Now, what happens during this phase of inflation is that you have a transition between those two regimes. So the typical models of inflation that we now work with and have been confirmed by the data are such that the Hubble radius, this wavelength which characterizes the curvature of the universe, is almost constant during inflation. And so if you compare it with the wavelength of a given Fourier mode, which grows as an effect of the expansion, then you find that there are essentially two regimes. The first regime at early time, when the wavelength is smaller than the Hubble radius, that's the flat space-time limit. You don't feel the effect of the curvature, and nothing in particular happens. And then at some point, those scales, they cross out the Hubble radius, so they become what we call super Hubble, larger than the Hubble radius. And there you start to create particles through the mechanism I was explaining. And this mechanism is super efficient. I will give you more precise details in a minute, which means that those particles, they turn into classical fluctuations of the density field later on, which then evolve and form the large-scale structure of the universe. Okay, so that's the standard paradigm that most people work with, that density fluctuations, they form from quantum fluctuations which are amplified by gravitational instability. One way to test this mechanism is through measurements of the cosmic microwave background, which is something which happens at the beginning of what is called the matter era, so when the universe is dominated by pressureless matter. This is a map which I guess you have seen various times of the temperature fluctuations of the cosmic microwave background as measured by the Planck satellite. And those are really the oldest picture we can take of those tiny fluctuations. They are very small. Okay, they are of the order of the tens or hundreds of micro-Ks for an average temperature of the order of 2.7 K. So they are still very small at this stage in the universe. They will later evolve and grow in size, in amplitude. But they are the direct imprint of those quantum fluctuations in the early universe. So how do we describe it in a bit more technical way? So usually we proceed as follows. So in order to realize this phase of inflation, there are many different models. Okay, I won't be specifying one model in particular. The simplest models that we work with, they rely on a single scalar field, which is called the inflaton, which I denote here by phi. So matter is essentially one scale field, and then you have the metric, g mu nu. So on top of this homogeneous and isotropic expanding background, you can introduce fluctuations. Those fluctuations, they will be described by delta phi and delta g mu nu. And as it turns out, there is a single combination of those guys, single scalar combination of those guys, which propagates in a gauge invariant way. By gauge invariant here, I mean independent of the choice of coordinates. You know that GR is a theory that is independent of, that is invariant under diffeomorphism, so changes of coordinates. But there is one combination you can construct which does not depend on the choice of coordinates, which I will call V, and which is directly proportional to the temperature fluctuation that we measure on the cosmic microwave background at large scales. Okay, so this V is really my physical field, which describes fluctuations. And the idea is that this V field, I'm going to quantize it. Okay, so of course, I don't quantize the full metric, because this is not something I know how to do, but I just say that at the background level, space-time is classical and obeys the classical laws of GR, and I just quantize the fluctuations on top of this homogeneous background. So V becomes a quantum operator, and starting from some vacuum state, which I will specify in a few minutes, then I can compute the evolution of the quantum state of this V field and compute expectation values of V at the end of inflation, and then compare it with data, and everything works very well. Okay, so here on the bottom of the slide, you have the power spectrum of the temperature fluctuation as measured on the cosmic microwave background. The blue points are data points, and the red curve is the theoretical prediction, where only 6 parameters are being fitted, and you see that the agreement is excellent. Okay? On the left, it's the temperature correlation. On the right is the correlation between the temperature and the polarization, the so-called E mode of the polarization of the CMB photons, and the agreement is very good. Okay, this is the E mode correlation. Okay, so that's the standard story. That structure formation proceeds from the gravitational amplification of quantum fluctuations. But even though it provides a very good agreement with the data, I think it's not such a trivial statement to make. First of all, because it relies on using quantum mechanics on cosmological scales. We have never tested quantum mechanics at those scales. We have tested quantum mechanics mostly in the lab, but not really in the universe. So is it a theory we can trust up to those unknown scales? This also comes with a number of open issues. So one is, okay, can we trust quantum mechanics at those scales? Is it legit to quantize only metric fluctuations, this procedure of splitting classical background plus quantized fluctuations? Is it something I can do even for the gravitational degrees of freedom? We don't know what quantum gravity is, so it's maybe not obvious that I can do that. There are also questions related to the so-called quantum measurement problem, which is the issue of starting from a quantum superposition. If I perform a measurement, the wave function is supposed to collapse towards the outcome that I measure, and it's not exactly understood, or say different people have different opinions or different takes on exactly how this proceeds. Usually, the solution is relies on saying that, okay, the system collapses under the measurement performed by an external observer. But in the case of the universe, it's the wave function of the entire universe, so there is no external observer by definition. So what does it mean to perform a measurement? How does the universe measure itself? Does it make some sense to even ask such a question, and so on? So there are some fundamental issues related to using quantum mechanics for the entire universe, which, by the way, is also a way to test quantum mechanics itself. So it's something which I will not discuss today. but it's also something that I'm working on to use cosmological measurements to test some alternatives to the standard formulation of quantum mechanics. One additional remark I would like to make is that here I will discuss this issue in the context of inflation for explicitness, but in fact, exactly the same issue and the same considerations would apply for alternatives to inflation, because most alternatives to inflation, they also rely on exciting quantum fluctuations out of the vacuum and using gravitational amplification. Okay, whether this is done during a phase of inflation or during a phase of contraction, followed by a bounce and so on, this is always the same mechanism. So this will equally apply. So my point of view here is that, in fact, it's a strong statement to say that structures form from quantum fluctuations, and because it's a strong statement, we should require some strong evidence. What people most of the time implicitly sort of assume is that the consequences that we can infer from this idea are consistent with observations, and indeed they are. And so they take it as some indirect confirmation that the scenario is working, which is indeed an indirect confirmation. But the question I want to ask is that, okay, is there any direct evidence? Is there something we can test in cosmological fluctuation that would tell us that they come from a quantum mechanical process? So it's not a new topic, okay? It's not, people have been working on that for a long time. There have been some revivals throughout history of cosmology. I'm not going to present everything. I'm just quoting a few names at the bottom of the screen who I think are some of the people who worked on this mostly. But so I will have to make some choices, of course, but just, okay, keep in mind that there is a variety of approaches and works on this matter. Okay. So first of all, how can we distinguish quantum explanation from, say, a classical explanation for cosmic structures? Well, the quantum and the classical world, they mostly differ by the nature of the correlations they allow for. The recent Nobel Prize is a very good example of that with Bell inequalities, and I will discuss Bell inequalities in practice. But the more generic question I want to ask is there something quantum in the correlations, right? So if I just take my density field in the universe, I measure it at different locations, can I construct some correlation functions, some observable, that would tell me whether those fluctuations, they come from a quantum process or a classical process? And people have tried to answer this question in quantum information. So outside the field of cosmology, it's a very generic question, which has nothing to do with cosmology in particular. So people working in quantum information theory have tried to come up with theoretical answers to those questions. And one of them is called quantum discord, which was proposed already more than 20 years ago, but on which people are still actively working to understand exactly all the implications. So what I'm going to do first is to introduce this tool and then apply it to the cosmological field to see what it gives, before trying to explicitly construct some Bell inequalities or stuff like that, but just to see in theory, is there something quantum in the correlation that we should try to harvest somehow? So the idea is pretty simple. So you take a system, you split it between two subsystems A and B, and the state of A can be in any of those configurations AI, the state of B can be in any of the configurations BJ. And then I want to measure, or I want to characterize the correlations between A and B. So if I do it in the classical description, I would just introduce some probabilities associated to AI and BJ, which I call P of AI BJ. I can define the probabilities of the state of A only by just summing over, by just doing marginalization over the state of B. Okay, so P of AI is the sum of the joint probability over all the possible configurations of B. I can define what is called the Van Neumann entropy, which is just the sum of P log P, which measures the uncertainty I have about the state of A. So if the Van Neumann entropy is 0, then it means that one of the A's here is 1 and all the other A's are 0, so I know the state of A for sure. If I don't know anything about the state of A, the entropy here will be larger. And then I can make use of something which is called the Bayes theorem, which just tells me that the entropy which is contained in A in B is equal to the entropy contained in B plus the entropy contained in A once I know the state of B. Okay, it's just a classical law of standard probabilities. So now if I try to reproduce those considerations at the quantum level, so at the quantum level I would describe AB by a density matrix, not by a probability. But I can still define the density matrix of A by tracing over B. I can still define the Van Neumann entropy. It's the trace of rho log rho instead of sum of P log P. I still have the fact that if the entropy contained in A is 0, then it means that you can show that it means that A is in a pure state, which means that, okay, the state of A is known for sure. It's in a given pure state. However, this rule, which I had on the left-hand side, is violated. Okay, so S of AB is not equal to S of B plus S of A knowing B. So why is that true? In fact, so of course there are some mathematical theorems behind that I'm not going to show. Just to give you like some physical intuition of why this is true. So you can consider this well-known state, okay, which is called the EPR state, two spin particles, A and B, and I consider the entangled state where the two particles are up and the two particles are down. This is a pure state, right? So the entropy in AB is equal to 0. I can compute the reduced state of B. I just do psi. This will give me the density matrix. I trace over A, blah, blah, blah. There is some calculation. It gives me a diagonal matrix, a 2x2 matrix with 1/2, 1/2 on the diagonal. And then if I do rho log rho, and I take the trace of that, I find log 2. And this means that this equality cannot be satisfied because S of AB is 0. S of B, I said, is log 2. The entropy is always a positive number, so clearly this equality cannot be correct. Okay, so the idea is to use the violation of this rule as a measurement of the quantumness of the correlations. Okay, so for two subsystems A and B, I take S of A knowing B plus S of B minus S of AB. Okay, so right-hand side minus left-hand side. You can show it's always a positive quantity. And I define this as being the quantum discord, so a measurement of the quantumness. Yes?
Is there equality in general?
Inequality? Yes, so this guy is always positive. There is a lower bound, which is 0. There is no upper bound. It can be as large as it wants. There is just one non-trivial thing in this formula, which you may have noticed, which is the pi j here. And this has to do with measurements in quantum mechanics, okay? Because how do I define this S of A knowing B? It's the entropy of A once I have measured B. But measuring something in quantum mechanics is not something trivial. It's a projective measurement. So if you have the different probabilities to find different outcomes. Depending on the outcome, the state of B becomes something different. So you can measure B along a set of complete set of projectors, which I call pi j. And usually we minimize, it's a technical thing, but we minimize over this set of projectors in such a way that if we find a non-vanishing discord, it's not due to a bad choice of projectors to measure B. It's really due to, for any projector, for any way of measuring B, you will find a non-vanishing discord. Okay. In practice, technically, this minimization step is most of the time technically very difficult. So this is what makes the calculation of discord hard. Of course, I won't show any concrete calculation, technical calculation. It's just a technical detail, but it just allows me to make the statement that if I find a non-vanishing discord, then there is something quantum in the correlations. Okay, so now my goal is to apply this quantum discord tool to cosmological perturbations. So as I was saying before, the metric, I can expand it over a homogeneous anisotropic geometry, delta G mu nu, which becomes a quantum operator. The matter field is also expanded in the same way. And as I was saying before, there is a single combination that is invariant under different coordinates systems. And which propagates in the theory, which I call the V. So I can start from the Einstein-Hilbert action, where I put a scalar field. I plug this decomposition into the action. I expand at quadratic order. And then I obtain the following Hamiltonian. So let me just explain a bit the different terms in this Hamiltonian. So first of all, you see that the Hamiltonian is just a sum of different Hamiltonians, one per Fourier mode k, which means different Fourier modes decoupled, which makes sense because I work at leading order in perturbation theory. If I worked at cubic order, I would have mode coupling, but at leading order, all the Fourier modes are independent. So CK and CK dagger are annihilation and creation operators. Okay, usually they are called A in quantum mechanics, but here A is the scale factor, so I just use a different notation to make sure there is no confusion. And there are essentially two terms in this Hamiltonian. The first one is a free term. You see, I either create a particle with K and destroy it afterwards, or create a particle with minus K and destroy it afterwards. So that would just describe oscillations on a flat spacetime. This term would be here in a flat spacetime as well. And then I have this second term, which is the non-trivial one, and which is an interaction term because between quantum fluctuations, represented by this CK, C minus K, and so on, and the classical background, which is controlled by this combination here. So A is the scale factor, which I have introduced before. Epsilon 1 is just another function which describes the rate at which the universe expands. Okay, so it's minus h dot over h squared. It does not really matter what this guy here is, just a function of the background. Okay, so it depends on the way at which the universe is expanding. If the universe is static, so scale factor is a constant, then this term here is 0, and there is not this second term. Okay, this second term only arises as an effect of the expansion. And you see that what it does is that it either creates a pair of particles with, oops, sorry, wrong button, with K and minus K. Okay, because of statistical isotropy, if you create a particle with K, you need to create a particle with minus K. Or it destroys one particle with K, one particle with minus K. But this guy will be responsible for particle creation, which I was mentioning before. Oui?
So you said that this is important that the universe is dynamical in this story. So does that mean that in pure de Sitter we wouldn't have this effect?
Yeah, so in pure de Sitter, the scale factor is not static. Is growing with time. So this guy here is not 0, and so maybe epsilon 1 is the...
Yeah, this is what I was confused about, because epsilon 1 in the Sitter, epsilon 1 would be 0, right?
Yeah. Okay.
But in that limit, you say that it works anyway. Okay.
So the Sitter, pure de Sitter is a bit singular,
okay.
Because scalar fluctuations on the Sitter are you can go as close as you want. Epsilon 1 appears both in the numerator and the denominator. So obviously, if you take it to 0 in a continuous way, you can approach a finite limit. Yes. But if you want to set epsilon 1 equals 0 from the beginning, then you run into some...
And I had forgotten that A was in the... Okay, it's fine.
Exactly, yeah. It's the ratio of... So now I have a Hamiltonian. So I can solve Schrödinger equation. I have one Hamiltonian per Fourier mode, so I have one Schrödinger equation per Fourier mode. And if I start from the vacuum and deep psi over dt is the Hamiltonian times psi. So if I solve that equation, I obtain the wave function of this V field. And what I find is the following. So I have one wave function per Fourier mode, so one psi per Vk mode. And I find that any time t, it's given, I can expand it in Fock space in this way. So you see it's a sum of states which contain n particles in K and n particles in minus K. Again, because of statistical isotropy, I must have the same number of particles on both ends, both with K and minus K. And then there are some coefficients in this sum which depend on two parameters, r and phi, which are called the squeezing parameters for a reason that I will explain in a minute, and which equations of motion that have no importance for you, but which are just given by the background. Okay, so if I know the rate at which the background is expanding, I know I can compute this a square root of epsilon 1 function, and I know the functions which appear in these couple differential equations, which I can solve. That will give me the time evolution of r and phi, which I can replace here, and that gives me the state at any time in the evolution. So this is a plot of what you get for a given background, which is quite close to the Sitter. Time here is labeled by what is called the number of e-folds, so it's the log of the scale factor. So as the universe expands, time goes from left to the right. And you see that the squeezing amplitude in particular, this R parameter, is initially very close to 0. So if R is close to 0 because of the hyperbolic tangent, all the terms in this sum are 0, except from the n equals 0. N equals 0 is just the vacuum state. Okay, the state with 0 particle in k, 0 particle in minus k. So initially, I start in the vacuum state. And then there is a time where A equals A star. A star corresponds to the value of A when the mode becomes super Hubble. So lambda, the wavelength of the mode, becomes larger than the Hubble radius. And in this regime, you see that R starts to grow, which means that I start to populate states with a higher and higher number of particles, and which just means that I create particles. Okay, so it's this particle creation mechanism that I was mentioning before. Okay, so at early time, there is no particle creation, and I stay in the vacuum state. And then at late time, I create many, many particles. And here there is phi as well, which I'm not going to comment on. So those states are known, very well known by people doing quantum optics in particular. They are called two-mode squeezed states. And the level of, so why are they called squeeze states? I will explain in a second. But just to mention that the amount of squeezeness is measured by this parameter R. R in inflation is equal to more or less to the number of E-folds that, so to this log of A over A star, basically. And at the end of inflation, is proportional to log of A over A star. And at the end of inflation, log of A over A star is of the order 50 for the scale that we see in the cosmic microwave background. Just so you know, in the lab, people working in quantum optics, they manage to create very squeezed states. Most squeezed states they can form, they have a value of R which is of the order of 5. I think now they reach 5. And it's a logarithmic scale. Okay, so 50 is really, really more than 5. So it means that this is really probably the strongest squeeze state that, okay, here is a provocative statement because I cannot be sure, but probably one of the strongest squeeze states that has ever been created in nature. Okay, it's really, really squeezed. So why is it called, before addressing that, let's just directly jump to the result of the computation of quantum discord. So this state here is an entangled state because I have correlations between particles in k and minus k. And so if I compute quantum discord, I find the following result. So it's a rather long calculation, but at the end, the result is very simple. It collapses down to this formula, which does not depend on phi. It only depends on R, and it's given by this combination. Okay? So if you plot it as a function of R, when R goes to 0, this goes to 0. So in the vacuum state, the quantum discord is 0. But when R becomes large, it becomes proportional to R. Okay, so the upshot here is that during inflation at early time, squeezing amplitude is very small, so quantum discord is very small. Nothing interesting happens. But when the wavelength of the mode crosses the Hubble radius, squeezing starts to operate, R starts to grow, and as a consequence, quantum discord starts to grow as well. And again, the amount of discord is very large. If you take this 2 over log of 2 times 50, you find something which is of order 150, which is probably the most discordant state produced in nature, because in the lab, they can never reach such amount of discord. So this gives a first indication, which is rather encouraging, and which suggests that, yes, sorry.
The system A and the system B, it's A, it's K,
Yes.
the number of...
For the moment, yes.
And,
Yes,
and
yes.
B is minus K.
Exactly.
Okay.
Exactly. So this is a very good remark. So here I'm interested in the correlations between K and minus K, which is not what I measure. Okay, because I measure, in practice, I measure something in real space. Okay, so I will come to that a little bit later on. It's just simpler to to introduce it first in Fourier space, but you're right. Here, those are correlations in Fourier space, which are highly discordant. And that gives me confidence that a priori there is something very quantum in the state in which cosmological fluctuations is placed, right? They are placed in a state which is very, very discordant. And so potentially there is a lot of quantum stuff that I can measure. At least that's what this calculation is suggesting. And so a natural question would be, well, can I try and violate some Bell's inequalities, for instance? So let's jump to Bell inequalities. So here I have a priori everything I need. So just I guess everyone is familiar with Bell inequalities, but the idea is that in the standard Bell experiment, you produce two entangled particles with some spin degree of freedom, for instance. Each of them is measured by two observers, Alice and Bob. They measure the spin in different directions, which they choose, without letting the other one know which direction they picked. And then they cross-correlate the result, and they construct this combination of the measurement of the spin in different directions. And you can show that in the local hidden variable theory, this B combination should have an expectation value that is less than 2. So when they repeat the experiments many, many times, they compute the ensemble average of B. They should find a combination which is less than 2. But in quantum mechanics, this can be violated. Okay? So B can be larger than 2, in which case you have shown that you have excluded local hidden variable theory. So here we have a priori everything we need to construct a Bell inequality. We have a bipartite system, K and minus K. It's an entangled, they are placed in an entangled state. A two-mode squeeze state is an entangled state, very discordant, very squeezed. So maybe we have everything we need. Now there is one technical subtlety which people have stumbled upon for a few years, which is that in fact, if you want to violate Bell inequalities, it requires to construct operators which are a bit non-trivial. And this has to do with a statement made by Bell himself, in fact. So Bell himself wrote in a paper that is almost unknown that it's impossible to violate Bell inequalities with states which have a positive Wigner function. So I will explain now what it is and why Bell was thinking that there was a no-go theorem here. So let me just mention a bit the Wigner function. So the Wigner function is a function in phase space. So V is my cosmological fluctuation. P is the conjugated momentum. So you see the fly is trying to point in. Maybe I can drive the fly crazy. I don't know. So it's a function in phase space which I construct from the state. So if I know the wave function, I can apply this transformation, which is called the Wigner-Weil transformation. And I can construct this function in phase space, which is just another representation of the state. Okay, I can represent a state with a wave function, or with a density matrix, or with a Wigner function. Those are all completely equivalent. And it so happens that if I compute the Wigner function for the two-mode squeeze state, then I find the Gaussian function. W of Vp becomes a Gaussian function, which is why the two-mode squeeze states are called Gaussian states. And this Wigner function has a number of interesting properties. So the first property it has is you can compute the time evolution of W. Okay, W is just some integral of psi. D psi over dt is given by Schrödinger equation. So you can compute dW over dt. And then what you find is that it's given by the Poisson bracket between itself and the Hamiltonian of the theory. So what does this, so this is just the Liouville equation. What does it tell me? It tells me something very simple to interpret physically. So here is a plot of the Wigner function in Vp, in the Vp space. And on the right side, what I have done is to take this function, which is a positive function. Because it's a positive function, I can, just for the sake of the argument, I can see this function as a distribution function, just for the moment. So I can draw points randomly in phase space according to that distribution function. Okay, and now what I will do two things. I will evolve this Wigner function just using the Schrödinger equation on the one hand. And on the other hand, I will take each of those points. So here I've drawn, I don't know, maybe 1,000 points or whatever. So each of those points, I'm going to evolve them with the classical equations of motion. So just the Hamilton's equations of motion. And when I do that, I obtain the following. So both functions sort of rotate in phase space, and they get squeezed, very squeezed in one direction, very spread in the other direction. This is why we call it a squeezed state. And the fact that W obeys this equation is essentially telling me that the cloud of points on the right-hand side evolves in exactly the same way as the distribution function of the left-hand side. So in fact, W is really acting as a distribution function, at least from the point of view of its time evolution. It just evolves as the distribution function of classical processes. So this is first property. And the second property that it obeys is that, in fact, I can use it to compute any expectation value of any quantum operator. exactly as if it was a distribution function as well. So the way it works is, sorry, I don't know why it's, okay. The way it works is the following. You define, so for any quantum operator A, you can define what is called a Weil transform, which is also a function in phase space. And then the expectation value of A is always going to be given by the convolution between W and A tilde, the transform of A. So it's really as if W was acting as a distribution function. And this is why, in 1986, Bell himself said that, Bell inequality validation requires non-positive Wigner function. The idea here is that if a state has a positive Wigner function, in fact, it can be entirely described with a distribution function, so there is nothing quantum in it, and that's the end of the story. Unfortunately for us, the state of cosmological fluctuations is a two-mode squeeze state. It's a Gaussian state, which has a positive Wigner function. So according to Bell, I should stop my talk here, okay? It's a dead end. But in fact, it was later noticed in another paper, which is also not very known, and I think it's a shame because it's a great paper, by Revzen in 2006, that in fact there is a way out of this theorem, which is to use what is called improper operators. So it's a little bit technical, but improper operators are operators which are such that when I compute the Weil transform using this formula, I obtain a function which sometimes takes values which do not belong to the spectrum of the quantum operator. Okay, so A hat has some eigenvalues, it's a quantum operators, but sometimes the Weil transform can take values outside the spectrum. And when this, so of course this does not happen for most of the quantum operators you know. Most operators are proper, but some of them are improper, and if you use them, there is a theorem that tells you that you might violate Bell inequality. Okay, I just checked time a bit, yeah. So let me just show how it can be done in practice. So another thing, I don't know why the pointer keeps changing, but I think as long as you can see it, it's okay. So thank you very much, thank you. Another thing you have to do is to construct a spin-like observable, which is not obvious for us because what we measure is a temperature fluctuation. Temperature is a continuous variable. So we need to convert a continuous measurement into something which looks like a spin measurement. But this can be done as follows. So you start from some position variable, which I call Q to be generic, which has a continuous spectrum. Then you can always divide the continuous spectrum into some intervals with a given size, which I call L, which you are free to choose the way that you want. And then you can perform measurements of Q and return +1 or -1 depending on the interval in which you fall. Okay, so quantum mechanically, this can be written as follows with some expression which depends on the Ketz and the Braz of Q. This I call SZ. SZ can take either +1 or -1 as a value, so it's a spin-like operator. And then you can generalize this construction to Sx and Sy by introducing S+, where you just shift the bra by L. And Sx and Sy are the Hermitian and anti-Hermitian parts of this S+, blah, blah, blah. You can work it out and find that if you compute commutators between those guys, then you recover the same algebra as the spin operators. Okay, so they are called pseudo-spin operators. They will allow me to violate Bell inequalities because everything relies on those, only on those commutators in the Bell inequality calculation. But they can be applied to continuous variables. That's the advantage. Also, you can show, by just a small remark, that some of them are improper. So this is the expression that I find for the Weil transform of those operators. So you see, for instance, SZ. SZ takes values which are either +1 or -1. +1 or -1 are the eigenvalues of the SZ hat operator. So SZ is a proper operator. But Sx and Sy, they can take any value between -1 and +1. They have a continuous spectrum. And so they can take values outside their spectrum. And therefore, they are improper, which is required according to this paper by Revzen. OK, so this is the result that you get. So let me describe those two figures step by step. So on the left-hand side, you have a plot of the expectation value of the Bell operator. As a function of L, L is the size of the interval. You can choose L to be whatever you want. And different curves here, they correspond to different two-mode squeeze states, so different sets of values for R and phi. And what you see is that there are some values of R and phi, for instance, this curve which goes down here, for which you never violate Bell inequalities. So expectation value of B is always smaller than 2. But there are some other values like this guy here, the light blue curve, which goes well above 2. Okay, it cannot be above 2 square root of 2 in quantum mechanics, you can show. But here, this curve violates Bell inequalities. Okay, so there are two mode squeeze states for which you violate the inequality and other states for which you don't. And that depends on the value of R and phi. And that also depends on the value of L. So what I've done on the right-hand plot is that I've optimized this L. So for every value of R and phi, I choose the L which maximizes the violation of the Bell inequality. And then I plot the value of expectation value of B in this plane R phi. So everywhere the color is dark blue, it means I have no violation. Okay, maximum value of B is always 2 because asymptotically you can show that for low L you reach 2. So this is just here is 2 just because of this low L limit, but this means there is no violation in this region. But in this region, it means that I can find a value of L for which there is a strong violation. Okay, so essentially what you find is that the states which violate Bell inequalities, they have a large squeezing amplitude and a small squeezing angle. Now, of course, the question is, okay, now take the state produced during inflation. Where am I in this plot? And so I don't know, you probably don't remember, but in the plot that I showed at the beginning where I had the time evolution of R and phi, during inflation, R increases, but phi decreases. So in fact, you go along a line a bit like that. So the details depend a bit. And in fact, you can show that if you work in a space-time which is very close to the theta, as you were mentioning before, okay, so which is in agreement with the data because the CMB tells us that we are close to the theta during inflation. In fact, if I go exactly to the de Sitter limit, the time evolution of the state exactly falls on the white dashed line. And the white dashed line happens to be, for something which is to me a bit, there is maybe a deep reason, but for me it's a coincidence, is exactly the asymptotic expression for the boundary between those two regions. Okay, so what, of course, we are not exactly, inflation did not take place exactly on the theta. There was a small deviation away from the theta, now we know, through CMB measurements. But it means that the way that you differ from the theta will tell you whether you are a little bit above the white dashed line or a little bit below the white dashed line. And okay, and as it happens, if you take the most favored models, or the ones which now are preferred by the CMB data, there is a preference for falling below the white dashed line, okay, which is, I don't know, lucky for us. So it means that at least in those models, instead of going along the white dashed line, you go into along a line which is a little bit tilted. And so when R goes to 50, in fact, you can be very deep in the dark red region, and then you might expect very strong violations. Okay, so that also gives sort of hope. So let me just check maybe I should wrap up. We started at 11 or 11? No. Okay. So let me just, yes, sure.
Does being on one side or the other of the white line correlate with any cosmological observables in particular, like, I don't know, spectral tilt or something like that?
Yes, in fact, it correlates with the running of the spectral index, pretty much. Right. And yeah, that's right. And so in plateau potentials, it's a combination of two, of the spectral index and the running. And in plateau, in potential functions with a plateau, which seem to be preferred by the data nowadays, this combination of running and spectral index is such that you go downwards. In large field models of inflation, that used to be preferred, that used to be compatible and very simple, so pretty attractive, then you would move up, so you would not violate. Yeah. So, but it means that you have, okay, it's a little bit, the answer becomes model dependent somehow. It depends on the details of the inflationary dynamics. Okay, so yeah, maybe if I can mention at least, okay, let me try to mention two more ideas. The first one is related to the question that was asked, I don't know, 30 minutes ago, which is that what I've talked about is a very simplified picture, where I just consider correlations in Fourier space. But in practice, we don't measure correlations in Fourier space. We measure correlations in real space. And in fact, even if you could measure correlations directly in Fourier space, what you could tell me is that, Bell, one of the assumptions of Bell inequalities is locality. Locality is a concept which is defined in real space, by definition, not in Fourier space. So I can have a theory which is local in real space. But, of course, when I move to Fourier space, I can mix modes in a non-local way. So there is no reason why my theory should be local in Fourier space. So even if I manage to violate Bell inequalities in the way that I've presented, I will just have shown that the theory is non-local in Fourier space, but okay, there is no reason why it should be local. So the reason why I started this way is because the Fourier space structure is very simple, different Fourier modes decoupled. So now I will move to real space. This will become a little bit more dirty, so to speak, but at least if there is a huge amount of quantum correlations in Fourier space, maybe it gives hope that some of it will also be there in real space. Okay, so you can move to real space, and then what you find is that the following happens. So typically, let me consider two points in space, x1 and x2. And then let's say that I measure the temperature at x1 and the temperature at x2. So in practice, I never measure the temperature at x1 and x2 precisely. I do this with a measurement device which has some angular resolution, some spatial resolution. So in fact, what I measure is a sort of a coarse-grained value of the field in a small sphere or in a small region around the measurement point. Okay, so I measure like the value of the phi field in a small region which is centered at x1 and with a size R1, so W here is like a window function, which corresponds to the resolution of my apparatus. Now you can, there is a nice trick you can play. So if phi is a Gaussian field, if phi is a place in a Gaussian state, then you can rescale the field and choose the support of those window functions W in such a way that when you compute, you have phi 1, phi 2, you can also define the pi 1, pi 2 for the conjugating momenta. And you can choose those guys in such a way that the correlator, the commutator between phi 1 and pi 1 is equal to I, okay? And correlators, cross correlators are 0. So what this means is that if you make this choice of normalization, then those measurements at those 2 points are exactly as if you had just a two-particle Gaussian state. And then you can forget about this is coming from quantum fields and so on, but just work with 2 degrees of freedom standard quantum mechanics. And when you do that, you find the following. So it's a bipartite particle-like system. Because it's a Gaussian state, everything can be described in terms of a covariance matrix. So here the covariance matrix is a 4x4 matrix because I have 2 degrees. I have phi and pi here, and phi and pi there. You can relate the covariance matrix to the power spectrum of the field. This is some technical point, but if you know the amplitude of each Fourier mode, so if you know the power in each Fourier mode, you can compute the covariance matrix as some integral in Fourier space. And then there are some formulas you can use to compute, say, quantum discord. But one remark to make before doing that is that those covariance matrices do not describe a pure state. Okay, so a pure state, you can show that if you have a two-particle Gaussian state which is pure, then what is called the purity of the state, which is trace of rho squared, which is 1 for a pure state, is related to the determinant of the covariance matrix. And you can compute the determinant of this matrix, and in general, you will find that it's less than 1, which means that the state is not pure. So here you might say that doesn't make sense because you started from a field which is in a pure state. There is no environment. There is no other degree of freedom, which is correct. But here the thing is that I choose to focus only on the configuration of the field here and there. But the field is correlated in real space. So say the configuration of the field at x1 is correlated with the one at x2, but is also correlated with the value of the field there. And the value of the field there is excluded from my description. So formally, it's a little bit as if I had traced over the configuration of the field everywhere outside those two spheres. And this effectively creates a statistical mixture, okay, a decoherent state. So it's a bit like decoherence, but here it's decoherence from coarse graining rather than decoherence from tracing over additional degrees of freedom. But this decoherence, this effective decoherence mechanism is key and is really a pain in I don't know what, in the calculation, because in general, decohered states are known to feature a lower level of quantumness. Okay, so you know that if you do the double slit experiment and then you add decoherence in the process, then you stop seeing interference and so on. So decoherence is associated to essentially to less level of quantum signature, which is less. And this is what we find here. So from this covariance matrix, we can recompute everything we are interested in, like quantum discord, violation of Bell inequalities, and so on. And then what we find, I will just skip the slides to move a bit faster, but what we find is that the amount of discord is much, much lower, and violations of Bell inequalities are much more difficult to find. Okay, so there are still, you can still find some, then you really have to look at very specific areas in parameter space, and this becomes much more difficult. So in real space, things are not as easy. Just another, let me just quickly jump to another point I would like to make. Yes, which is this one. I'm a bit late, sorry. So people have come up, so Bell inequalities are usually formulated in the way that I've presented, but there are lots of different Bell-like inequalities. One of the difficulties in cosmology is that Bell inequalities, you have to measure non-commuting operators, spin in different directions, which are non-commuting operators. And in cosmology, we have essentially a position field, a momentum field. So the non-commutativity comes from those two guys. But during inflation, say the position operator is usually associated to what is called the growing mode, which is a function that grows as a function of time. And the momentum is associated to a decaying mode, something that decays, and which becomes very small at the end of inflation in most models. You can cook up some models where the two modes have similar amplitudes, but in most cases, there is a hierarchy between the two modes at the end of inflation, which means that it's super difficult to measure the decaying mode in practice. But the good news is that there are other types of Bell inequalities which rely on measuring only one operator. Okay, always the same spin operator, always in the same direction. But you don't do it in exactly the same setup as Alice and Bob. So let me just review them very quickly. So that the usual Bell inequality, which is called spatial Bell inequality, requires a bipartite system, and then but you have to measure spin in different directions. The assumption that you are testing is realism and locality. You can do something which is called the temporal Bell inequality, in which you measure the same spin operator but at different times. Here you can measure only one spin operator, which is good, but the drawback is that you don't test the same assumptions exactly as the Bell inequality. In particular, you're testing also for non-invasiveness, which is always much more difficult to ensure. There is this option which is called Legge-Edgark inequality, which consists in measuring the same in a single system. Okay, so you don't split into two subsystems. You take just one system. You measure the same spin operator, but at multiple times. So at least 3 times. But you can construct Bell inequality, Legge-Edgark inequality for 5, 7, and so on, as many measurement times as you wish. But the drawback is, again, that you don't test for exactly the same assumptions as standard Bell inequality. And finally, there is this option, which is called bipartite temporal Bell inequality, where you measure the same spin for 2 different subsystems, so at 2 different locations and at different times. And this last option here is good because you're testing for the same assumptions as the usual Bell inequality, but you can do it only with a single spin measurement. Okay, so we have looked at those two options at the bottom of the table. And in both cases, I don't describe the plots, but in both cases, we found that there are violations. Okay, but they are, again, a little bit more difficult to find in parameter space, so you have to fine-tune. So this may be the way to go. However, it also means that you cannot use only, say, the cosmic microwave background, because the cosmic microwave background is a measurement of the density field at a single time, the moment when the photons decouple from the matter. So here you have to measure things at different times. So it means that you would have to correlate, say, CMB measurements with the measurements of the large-scale structure at some smaller redshift. So whether this is doable technically or not, okay, I don't know exactly, but this is maybe the way to go. Okay, let me just finish here, recap a few things. So I'm not going to say things that I've already said. Let me just stress maybe one thing which I've not mentioned, which is that in everything that I've presented today, I was considering the two-mode squeeze state, which is a Gaussian state. And why do I have a Gaussian state? It's because I started from perturbation theory at linear order. So each Fourier mode decouple, each of them is placed in a Gaussian state. But of course, GR is a nonlinear theory. Even if the matter field has no self-interaction, there will be always nonlinearities from GR, from gravitational interaction. So if you work at higher order, then you have cubic terms and quartic terms and so on in the action. And those will create non-Gaussian states. And for non-Gaussian states, the story changes a bit. For instance, the Wigner function is not positive anymore. So even the argument of Bell that you have to use improper operators to violate Bell inequalities, this is not true anymore because you have states with a non-positive Wigner function. And so this is also maybe one direction that people have considered, but which I think there is still a lot to do here, which is to try to see whether in the non-Gaussian signals, which we have not detected yet, so of course it's a bit speculative, but if one day we measure non-Gaussian correlation functions in the density field, maybe there is something easier to try to find there regarding the quantum states. Okay, I think I am a bit late. Sorry about that. So I'll just stop here, and thank you for your attention.
We have other questions.
Well done.
Well, it's a very naive one. You have a single picture of the microwave background.
Yes, yes.
So when you talk about measuring correlations, you have to make some assumptions on the structure of what you are looking at. Because a single sample is, you don't have correlations on a single sample. So what are the assumptions you are making?
Yeah, yes, right. So the assumption is I have so within my picture, my snapshot of the density field, I have correlations between different regions in real space. And well, you have correlations between different spatial points, right? And you can and then the assumption is that you can compute. So there is some sort of ergodicity principle. If you take 2 points, so you can measure them at different locations in space. So you have to replace. So essentially, you replace ensemble averaging and standard quantum experiments by spatial averaging. Yeah. But as we do for when we compute the cosmic microwave background correlation functions, it's also what we do. In practice, we measure it in real space. So we do averaging over directions of the measurement. And the theoretical calculation is done by taking quantum expectation values. So we also trade one for the other. It's like repeating the experiments in different places.
I have a question regarding what you said. You need different time. I mean, it would be easier if you had different time.
Yes, yes.
But if you consider CMB polarization, you also have access to some kind of, time effects or time dependence that might be a way to do it.
Time dependent in the sense that it's not the same visibility function, or in the.
Well, in the sense that the polarization is somehow sensitive to
Yes.
something which is related to like phase space. You see phase space evolution, right? Velocity. Or
Yes. Yeah. No, it's a very good point. Yeah. So I think I have nothing clever to say but I think it's definitely something to.
So, but you have not explored this yet.
No. No one has explored it, and I think that would be very interesting.
Other questions? I actually have another one. If I understood correctly, all the reasonings on the Bell inequalities that you have made here in this work is based on the construction of some pseudo spin operators using, and these seemed pretty specific in the sense that it doesn't seem to be a unique way to create operators in that way. And so have people explored other ways of building such operators, and were there some that looked more promising, that maybe wouldn't need, will require you to have correlators at different times, for example? Or do you think that these different time correlators are the only way to go?
Yeah, no, it's a good question. So the construction I've shown is those pseudo-spin operators. They have been proposed by someone called Larson a few years ago. And to my knowledge, there are, in the literature, there are 4 people who have tried to construct pseudo-spin operators for continuous variables. And we've tested them, the 4 of them. And the 4 of them, they give of course, there are some differences, but they give similar results. But you're right that this construction is not unique, right? There is nothing unique in the way that I've constructed my spin operator. I can come up with other constructions, and people have. And So if you want to prove, for instance, if you wanted to prove an exclusion theorem that there is no way you can violate Bell inequalities, that would be much harder because you would have to, to show that there is no choice of pseudo-spin operators for which there is a violation, and that's a more difficult problem. Yeah. So there are a few constructions around, and the result doesn't seem to matter too much on which one you pick, but maybe maybe you can come up with something more clever, and
When you were mentioning K, I mean, it was just one dimension on K. I mean, there was no 3 dimensions.
Then it's a typo. It's really 3 dimensions. Maybe, okay. Maybe I did. Sometimes when I write P, like the power in K, P of K, I just use single K without an arrow because the amount of power is independent of the direction because of isotropy.
What is the difference, K, positive, negative? What does it mean?
Because of that. Yeah. So I mean, So the field that I measure, so the temperature field, is a real field. So when you move to Fourier space, it means that, say, if I look at phi minus k has to be the complex conjugate of phi k. They are related by that, which means that when you count your degrees of freedom in Fourier space, in fact, you have to focus only on half of the Fourier space, because the other half will be just given by, it will be just related through this formula phi minus k is phi k star. And that's why some of the integrals, they are integrated over what I call R3+. R3+ is just R3, but I just take the upper half plane, for instance. Yeah. But it's really, it's a technical thing. Otherwise, it's 3-dimensional calculation.
Okay, if we don't have any other question, I think we can thank Vincent again.
All right, thank you.
Thank you for coming.